I wanted to give a demonstration of how to use my learning stack editor. So here's kind of the scenario I'll paint for you. I've used a dog picker and it's picked a lot of objects. I have a manual picker run here that shows me there's actually about 595 particles in my 8 images here. Dog pickers picked 670, but if we take a look at the stack here, we can see that there's a lot of non-particles. Here, maybe let me set the zoom a little bit better so we can see a few more particles here. So it's picked it's picked a lot of good particles. It's picked a lot of ice chunks. It's picked a lot of carbon edge or something along those lines. So generally the stack isn't very clean. So it's always good to have a good set of centered particles for my learning stack cleaner. So I always recommend using the eMan Centiline IT program. If you're interested in learning more about this program, the link is right here. But basically what it does is it uses only integer shifts to center particles, and so it doesn't actually change any of the data. It just kind of shifts things around, even though it does kind of apply a mask, which is annoying, but nonetheless. So I'm just going to do the copy and paste command thing here. So I'm going to run the center particles. I only have 670 I think only 500 actually make it into this stack. So it actually runs fairly quickly. You can see it finished the whole operation in 7 seconds. So now I have a second stack with more centered particles. I always find it interesting to look. It said it kept 474 of the 503, which means there are 29 particles. That's like it's bad. I'm always kind of curious what these particles look like. Let's see here. Well, you could probably say that these are a little crowded, but basically the program couldn't find the center of the program, and we look at our good one here where I was able. You can see I had to shift this particle a little bit to try and get it centered, and the general trend is that our particles are generally more centered than they were before. I think this is really helpful for my learning stack creator. So you can see there's a lot of junk in here, and the goal is to kind of train my learning stack editor to select these particles. So to get the learning stack cleaner, I guess is what I call it, sorry, you click on here. I haven't set up any options, but the actual program contains several options. So we'll switch over to my VNC window. So here. Alright, because there's kind of 3 steps in the process. Finish isn't really a step, I guess, but the idea is that you need to kind of train your particles here. Okay, they're a little big. Let me be a little bin by 2. It's randomly taking these particles from the stack, so the order of which you get is always going to be different. I find that it's best to kind of zoom in on the actual particles here. So I mean, I think my haven't set up the clip, so it's actually post-binning clip. Okay, so now you can see the clip size is kind of zoomed in on the particle. I find that this is kind of the best thing. It is using a tan-H low-pass filter, so sometimes maybe a little bit more low-pass can be good. You're welcome to play with some of these other settings. -1 means the pixel limit's turned off. Median filter is given in pixels. Number of rows, number of columns. This tells you how many particles it displays on the screen at another time. This is a bug that I need to fix, but generally you can't see that particle. And so the goal of this step here is to kind of classify particles as being good or bad. So is that a good particle or not? Yeah, so that one's a bad one, that one's a bad one, that one's a bad one, that was a bad one, that was a bad one. The idea is 1 click makes it green, 2 clicks makes it bad. So if I click here once, 1 click, 1 click, 2 clicks, and it's basically I'm going through and assigning these things as being either good or bad. I probably trained enough at this point, but it's probably not going to do a good job. So when you're to the point now where you think you've trained enough, it thinks 16 assigned because I haven't refreshed. So I'll just refresh. So now it has 32 assigned. It says I've gotten 18 good and 14 bad, which is kind of the minimum I would say is theoretically is 4 and 4 or something like that. 4 good, 4 bad. But you know, we've gotten enough training. I usually recommend going to 150 particles, but let's train our picks so far and see how the prediction method is doing. So now what it's done is it's sorted the particles according to whether or not it predicts as a good particle or a bad particle. Green means good, pinkish means bad, and you can see it did a pretty good job. I would probably say that that is not a particle, that one is a particle, that one is a particle. Is that, yeah, okay, that's a particle. And then once you're good with the accepted predictions, you can hit the accept predictions, and then it kind of assigns the rest according to the prediction. So it allows you to train a lot faster. So that one's probably bad, good, 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 good. Ugh, bad. And then I'll accept the rest. So you can see I'm now working a little bit faster. As you start getting happy with the results, yeah, see there's some bad ones, but everything else I'll accept. Training takes a little bit longer than just refreshing, but if you want to update your assignment parameters, you have to do the train aspect. So I can accept. So I can do refresh, but then it didn't update with my good and bad criteria. So I'm going to say that one's bad because it's just way off center, even though it does have a particle in it. It's up to you to really decide what you think is a good particle and a bad particle. You know, sometimes we found that template pickers are better than humans at determining good and bad particles. I remember a ribosome data set. The human didn't pick as many good particles as a template picker, and they got higher resolution when they used the template picker. Or the doc, I can't remember what picker they used, but when they used the automated picker, they picked more particles, got higher resolution than when they manually picked all their images. So I'm going to train. You can see I'm now at 72 good and 40 bad. So that's a bad one, ice chunks. But everything else is pretty good. So, and I guess that's a good one. I was thinking that was bad. So I'll accept that. So now you can see we're getting closer. Maybe it's a good time to expand our search range. So this is where it gets a little crazy. I think I can hold 5. I have an autofit window, but it doesn't seem to be working on my Linux client right now, and I can probably go 11 wide. And so now you can see that it gives me a lot of particles. And if your particles aren't sorted, this window becomes overwhelming quite quick. And what it's kind of do is kind of shuffle down. So these are all in kind of the good range, and then oops, I think that's a good one. So you kind of basically you need to assign all the kind of intermediate ones, and then also find good particles in the bad section. And then you can say, oh, I think that's a chunk of ice. Then you can say accept predictions. And then it kind of fills in everything else. And now we have an updated data set. So let's train and refresh, especially it's a large one. So now I have 199 assigned, 125 good, 74 bad. And you can see, yeah, generally, you know, every now and then you get one pretty highly ranked piece of junk. So is that a good one? Do I have any good ones in the bad section? No. Except prediction. So now you can see I'm assigning particles at 50, I guess 55 in a chunk here. Now, the limit of my particles is only 474. It's a fairly small data set, but I've designed this program to work with, 100,000 particles. Maybe you only need to train, hopefully, 200, 300 or something like that. I'm curious to see some of the people that really take on some of these larger data sets with my program and what kind of bugs they'll find. So this is not an aligned stack. This is just kind of, now is that a top view of a cryo-EM? I don't know. There's some iffy things. So if you want to include more, I would include more when you're assigning these picks. If you want to be a little bit more selective, be more selective. Again, it's a learning stack editor, so it learns what you tell it is good. So now I've assigned like 300. You can see I have this class accuracy. And this class accuracy is basically when it's assigning the classes. It takes 80% to use the assumption, 20% are left out, and then it double checks those 20% to see if they are assigned correctly. So about 80% of them are good. Every time you train, you're going to get a different percent class accuracy, even if you haven't picked any new particles. So now it's 90%, just because a different 20% of particles are excluded. So there's some randomness there. The other thing you can do to modify whether or not the accuracy is, you get to go to the classify panel, and this is where it gets a little bit more technical. So I'll take a little bit of time to explain this. So this is the data that is given to the classification procedure. So these are the raw particle pixels. So let's say our pixels are 80 by 80 pixels. So this would be giving 6,400 pixels to the data thing. So I forget how this thing gets updated. Yeah, so there it was. So I just added 1,600 pixels because I added that. It's kind of a slow update. Image stats is where it gives like the mean, the median, the skew, the kurtosis, the standard deviation. Basically it's collecting a whole bunch of statistics on the image and it passes that out. So if you can kind of classify things. Rotational average, I found moving from giving all 1,600 pixels to just the rotational average was a huge improvement because your particles aren't aligned, so you're not going to get too much from the actual pixels unless you're using an aligned stack. But if you take the rotational average, it actually did pretty good of distinguishing between good and bad particles, or at least empty areas and filled areas. And to kind of provide a little bit more information, I include the horizontal average, which basically takes all the pixel and sums them up horizontally. So you get another 80 data points. But it just averages that. And I found that this has kind of been the most robust settings for me. I've tried it on a number of data sets. Other things I was trying out is the phase spectra and the power spectra. Most people are familiar with the power spectra. That's where you look at the CTF rings and so forth. So it's taking the amplitudes at each location. The phase spectra is the opposite, where it's actually looking at the phases. So if anybody has learned like Fourier transforms in a classroom setting, this would be like the color, where this would be the darkness of the spots. I thought that, we know that the phase information is typically better in EM. I thought maybe we could classify using the phase spectra. So this would give you all the phase spectra pixels, again 1,600 pixels. This one just uses the stats from the phase spectra. Again, the rotationally averaged phase spectra, the horizontally averaged phase spectra. Here we have the power spectra, so you should see your CTF unless it's been corrected. Statistics on the power spectra, rotational average of the power spectra, so you should get like the 1D plot of the CTF there. Horizontally averaged power spectra, which may be nonsense or may be interesting, but it's kind of included a whole bunch of things there. Like I said, the more things you have, they're updated. So now you can see the number of data points you have increases the time it takes to do the training and the calculation. So if you limit that number, it is a little bit more zippy. So this is kind of the default settings that I've had selected. In the training data, what we're going to do is we now reduce the data dimensionality, basically doing some principal components analysis, where it's looking at all the statistics that you're giving it as input and setting the principal components. And this, based on this algorithm is, maybe I'll show the about here. All right, well that's not working. Or maybe it popped another window below. Yep, all right, so I'll have to fix that button, whatever. But basically this idea is based off the Tmax particle picker from the Rubinstein lab. So what they did is they only include the good particles in their data dimensionality, and I've kind of found that that's true. They're actually doing the entire particle pixels, so they're kind of looking at eigenimages here. I'm kind of taking eigenimages of the stats and the rotational average and the horizontal average, if you want to think in the eigenimage space. So we're only interested in the good particles because you could pretty much say that the bad particles are all noise. If you're interested in including all particles, I include that. Or if you just for some reason want to classify the bad particles, that probably just failed miserably, but I leave the option in there. Then you have a choice of complete principal components, where I'll take all the particles that are picked, and as I understand, the random principal components only takes a random subset. I don't think it's too much faster, but I include it because maybe if you get into the large data sets, or if you decide to include a lot of input, like checking the first row of either of the columns, then it might be good to use the randomized. Number of components is the number of eigenimages, if you will, eigenvectors that it'll calculate. So maybe you can get a little bit better accuracy by using less or maybe a little bit more. I guess, so here's now 82%, but again, every time you train the classifier, you're going to get a different percentage here. So maybe if I change it to 7 and I hit train, maybe it improves to more of our 90% accuracy we were looking at, or sorry, 85. And the last one, I haven't introduced any different classification methods. It's all using a simple vector machine. I have looked into some other ones, but as of right now, I'm not going to get too much into the simple vector machine parameters, but there's a penalty parameter and there's a kernel coefficient commonly called gamma. You can actually auto-assign it if you want to use negative, just plugging in -1 here, uses the auto-assign thing, which I think is basically, it takes it as 1 divided by the number of components. So you saw that the default was 0.005 because the default was 20 components. If you switch to 7, I think they recommend switching to 1/7 or 1.14 or something like that. So that's kind of training the classifier. If this whole section confused you, how about you just stick to the defaults and have fun, and hopefully it does a good job. If it's not doing a good job of distinguishing good from bad, your sorting is not quite how you'd like it, then you might want to play around with some of those parameters. Any more good ones in the bad section? I'll put that as a bad one. Ooh, that's a tough one. It looks kind of broken, but I'll leave it in there. So, all right, so accept predictions, and let's train again. So you can see I still have 110 particles remaining, so technically I could pick them on 2 more screens, but let's just pretend that I've decided that this is good enough. So then I just go and you can actually save the picks to a file, fine. But really, all you can do is save and quit, or if you just say quit, or if you click the X here, it all does the same thing. So I was quit, and then what it does is it reads the particle data from the file, classifies the remaining particles, creates a new stack mean plot, which you can now view in your stack editor. So here is now my learning cleaned stack here. It does save the bad particles, so that might be a bad thing if you're, your particle's a big stack, for example. Let's take a look. So here's all the badly selected particles. Sometimes there are a couple are going to get through, because remember I left 110 particles for the classifier to decide on. But generally, mostly bad particles. Now we take a look at the clean particles. We should hopefully see really only particles remaining in our data set here. So it did a pretty good job, in my opinion. I've tried it on some other things. I just thought the cryo-EM data set was kind of a good demonstration of the technique. So from this, I was able to create 283. From here, I'd probably go on and do an alignment. I'm a big fan of the maximum likelihood, but the rely on 2D maximum likelihood alignment newly implemented has been pretty good. Everybody loves Isaac, but it's kind of only set up on our cluster system at the moment. Create templates and maybe go back and pick it again. Some molecules don't lend themselves to doing templates. But anyway, I think this is a good way to kind of clean your stacks up, especially if you're using dog picker. It has a tendency to pick a lot of gunk. So it's a nice way to kind of clean things up and get the particles you want. If you didn't like the centering aspect of the particles, you could always go back and one of the things I kind of always play around with is converting a stack into particle picks, where I can now take this stack here and convert it into particle picks and then go back and create a new stack that is not altered in that way. So there must be some other tools there kind of like recreate the stack. Nonetheless, I hope you enjoyed this video, and if so, I will present some more.